This is the fourth lecture on digital signal processing, and our topic for today is characterization and description testing of digital systems. In the last lecture, we had introduced the exponential sequence and the sinusoidal sequence, and we observed that a sinusoidal sequence, which is a cosine omega 0 n plus phi, is not necessarily periodic. We examined the question of periodicity of sinusoidal sequences, and we observed that it is periodic only if omega 0 by 2 pi is equal to a rational number, that is an integer divided by another integer. This is the condition of periodicity. And then we looked at the sampling process in two stages, and we showed by an example that the sampling frequency Fs must be greater than or equal to twice the highest frequency content of the signal, and if this is not obeyed, then there occurs what is known as aliasing distortion, which basically means that high frequencies pose as low frequencies, and that is the origin of the term aliasing. This has an effect on the band of frequencies that we should focus on. I told you that omega 0 is a normalized digital frequency. It is actually twice pi f0 divided by fs, and the range of omega therefore is to be restricted to omega less than pi. The magnitude sign is indicated because actually the band is minus pi to plus pi. Okay. So, magnitude omega between 0 and pi, that is our range of vision. Then we discussed operations on sequences, basically 3 or 4 of them, 4: multiplication, addition, time reversal and delay. And then we took an example of a schematic diagram of a digital system, and we showed that you can write the difference equation from the given diagram. Vice versa is also true, that is, given a difference equation, you can always draw a schematic diagram. The schematic diagram is a description of the hardware as well as software, and therefore it is a very useful form. Then we discussed some examples of digital systems. First, we took the example of an accumulator. Then we took an example of an upsampler. Incidentally, an upsampler is schematically represented like this. X of n is the input to an upsampler, and if the sampling is increased by the factor L, then the representation is an upward arrow, and the factor by which the sampling rate is altered or increased is indicated here, and this is y of n. Basically, we showed that this amounts to padding zeros, L minus 1 zeros between two consecutive samples, and therefore the nature of the signal is not altered. The signal is the same, but it is stretched with zeros in between two consecutive samples. In a similar manner, we can also think of a downsampler. A downsampler naturally shall have an arrow pointing down, and if the factor of downsampling is capital M, then y of n, the description of y of n is simply x of m n, all right, 0 otherwise, which simply means that a downsampler ignores m minus 1 samples between 0th and mth, between mth and twice mth. You see, y of n exists only for argument of x equal to 0, capital M, twice m, or on the other side minus m, minus twice m, and so on. In between 0 and the mth sample, there will be m minus 1 samples. It simply ignores. All right, this is the process of downsampling. We next take another example of a m point, example of a digital system, m point moving average system. The description of this is that y of n is taken as the average of the present value and the past m minus 1 values. Okay, it sums up, it is an accumulator in that sense. Accumulation is over x of n, the present input, x of n minus 1, n minus 2, n minus up to n minus capital M plus 1, that is the present sample and the past m minus 1 samples. It accumulates and then divides by capital M. This is why it is called a average, and it is moving average because as n changes, the samples also change. When you take n plus 1, you take the previous m minus 1 samples. So, as you move with n, as you move with time, the average also changes, and this is a very useful device for data smoothing. Suppose you have a given x of n, which is the true signal s of n, plus some noise. Due to some reason there is a disturbance on this. Then when you take a moving average, the noise component diminishes, and in an usual process where the number of samples capital M is large, the average of this would be equal to 0, all right, and therefore moving average system is also called a data smoothing system, and it is very much used in experimental observations. And this brings us to classification of digital systems. There are various kinds of digital systems. We shall look at the classification and then concentrate on a particular class of digital systems for the purpose of this class. First is, a digital system can be either linear or non-linear. Formal definition is, a digital system is linear if and only if x 1 2 leads to y 1 2. Of course, it is, the argument is n. The symbolism is x1, this arrow stands for leads to. x1, if x1 is the input, y1 is the output, x2 is the input, then y2 is the output, implies, which is indicated by an arrow with two horizontal lines, implies that an arbitrary constant alpha x1n plus another arbitrary constant beta x2n, that is, if you make an input by a linear combination of the previous two inputs, then this should lead to alpha y1 of n plus beta y2 of n. If this condition is obeyed, then the system is said to be linear. You notice that linearity implies two principles. One is called homogeneity homogeneity, which says that if the input is multiplied by a constant, the output is also multiplied by the same constant, that is x1 leads to y1. If x1 is multiplied by alpha, y1 should also be multiplied by alpha, which has a very important corollary, that is if alpha equal to 0, that is if you have 0 input, the output should also be 0. Okay? This is the principle of homogeneity. And the other principle that is involved is superposition, that is you superimpose two inputs alpha x1n and beta x2n, then the output should also be a superposition of the individual outputs. So, two principles, one is superposition and the other is homogeneity, and the system is linear if it obeys both of them, homogeneity as well as superposition. There are systems which obey homogeneity but not superposition, they are non-linear systems. Similarly, there are systems which obey superposition but not homogeneity. Okay? So, a linear system is one in which homogeneity and superposition, both principles are valid, and one of the important outcomes of this is that 0 input for a linear system, 0 input should lead to 0 output, but this is only a necessary condition, it is not sufficient, because 0 input leads to 0 output only implies homogeneity, right? It does not imply superposition. Therefore, it is a necessary condition but not sufficient. Homogeneity and superposition are necessary and sufficient conditions for linearity, which means that if a system disobeys or violates one of these principles, it is nonlinear. And very simple test would be, first thing to do, given a system, does 0 input lead to 0 output? If it does, then you proceed with further testing, not otherwise. If 0 input does not lead to 0 output, then the system is nonlinear, and you can stop further testing of it. You do not have to test superposition. Let us take several examples. One is y of n, it is the accumulator, summation L equal to minus infinity to plus infinity x of L. This is a linear system, because you put x1, x2, find y1, y2, multiply them by alpha and beta, superimpose, you will get alpha y1 plus beta y2. This is very simple. I mean, I do not have to carry out the steps. But look at this, the same system, as I told earlier in one of the lectures, can also be written as y of minus 1 plus summation L equal to 0 to infinity x of L. This is not a linear system. Why not? Because making x of L equal to 0 does not make y of n equal to 0. Making x of n equal to 0 does not make y of n equal to 0 because of the initial condition here. So, this is linear, but this is non-linear. In this characterization of the system, y of minus 1 is an initial condition, can be given any arbitrary value, but this nonlinear system shall become linear if y of minus 1 is equal to 0. Agreed? All right. Let us take another example. If you want to test this system by rigorous means mean you take alpha x1 plus beta x2. Okay. What suppose you make alpha x1 plus beta x2. What will be the output? Suppose this input we call it x3. What will be the output? It will be y3 of minus 1 plus summation alpha x1 L plus beta x2 L with L going from 0 to infinity. Agreed? On the other hand, alpha y1 plus beta y2 shall be equal to, shall lead to, no, I beg your pardon, alpha y1 plus beta y2 shall be equal to y1 of minus 1 plus y2 of minus 1 plus the same summation. Agreed? And these two are not necessarily equal, because y3 minus 1 is not guaranteed to be y1 minus 1 plus y2 minus 1, because these are initial conditions, can be set arbitrarily. By the same token, is this clear? But our first test was sufficient, that is xn equal to 0 does not lead to yn equal to 0. By the same token, if you have a system which is described by mxn plus c, it is an equation to a straight line, it is a linear equation, but it does not describe a linear system, because this is an initial condition, and xn equal to 0 does not lead to yn equal to 0. Agreed? A capacitor, an initially charged capacitor, is non-linear. Okay? It is a non-linear system. Initial flux, an inductor with initial flux is a non-linear inductor. Okay? So, this must be remembered. This is an equation to a straight line, but it does not describe a linear digital system. By the same token, if you have yn equal to, let us say, x of n minus 1 multiplied by x of n plus 1, this is not linear. This is not linear, because superposition is not valid. Okay? If xn equal to 1 for, if xn equal to 0 for all n, yn shall be equal to 0. Homogeneity is satisfied, but not superposition. You can write it alpha x1 plus beta x2 and show this. We next go to time invariance. Time invariance, because time has lost its significance in digital system, it is also sometimes called shift invariance. Shift invariance, because n minus 1 simply means shift to the right by one sample, shift to the left n plus 1. And however, we shall continue to use the term time varying or time invariant system. The definition is that if xn leads to yn, this implies a system is time invariant if xn leads to yn, implies x of n minus n0 leading to y of n minus n0. Looks very innocent, but there are systems in which it is a bit involved to be able to test whether the system is time varying or time invariant. We will take a few examples, but the interpretation of this is that the output waveform, whether the input is shifted or not, the output waveform is preserved. It is simply bodily shifted. If the input is shifted by n0 samples, this shift can be to the right or to the left. In other words, n0 is an integer. It can be either positive or negative. Okay? So, the output shape shall remain the same, and the shape, a plot of y of n versus n, is called the waveform, and therefore shift invariance or time invariance is also an waveform preserving transformation. Is the point clear? The waveform, the shape of the signal over n remains the same. Now let us test a couple of one example at least for time invariance. Let me mention that the combination of linearity and time invariance, if a system obeys both linearity and time invariance, is called an LTI system, and LTI digital system shall be our focus in this course. Okay? We shall mainly be concerned with LTI digital systems. Wherever a nonlinear or time varying system we deal with, we shall point it out specifically. If nothing is specified, then you take it that it is an LTI system. Let us take this, my favorite example of an upsampler. An upsampler, as you have known, is described by x of n by L. Capital L is the sampling rate increase factor for n equal to 0 plus minus L plus minus 2L and so on. It is 0 elsewhere. So, x of n leads to x of n by L. Call this n by L. N by L has to be an integer for the signal to exist. So, call this as p, alright, small p, which is an integer. Then x of n minus n0, if it is shifted, should lead to x of p minus n0. Alright, it is the argument of x which is shifted by n0, and this is equal to x of n by L minus n0, whereas y of n minus n0 is equal to x of n minus n0 divided by L. This quantity and this quantity are not the same. They are not equal. Isn't that right? One is n minus capital L n0 divided by L, and the other is x of n minus n0 by L. They are not identical, and therefore the shape of the waveform is not preserved by the delay. So, it is a time varying system. Similarly, you can show that the downsampler is also a time varying system. Question: is the upsampler a linear system? Is it a linear system? It is a linear system. You take x1, x2 multiply by alpha and beta, you get the same result. So, it is a linear system. To understand this concept a little more carefully, a little more in details, let us take an example. Suppose we have an x of n which is like this: 1, 2 and 3, 1, 2 and 3. This occurs at 0, 1, 2, n. Suppose this is my x of n. Then if I upsample it by, let us say, a factor 2, then what will happen? In between two samples we shall have a 1 0, alright. L minus 1, 2 minus 1 is 1, and therefore upsampling by a factor 2 will mean the waveform becomes, this is y of n, 0th sample shall be preserved, then at 1 there shall be a 0, at 2 there shall be a sample of amplitude 2, alright, then another 0, and at this is 0, 1, 2, 3, at 4 there shall be this sample 3, 4. So, this is the upsampled version of the input waveform, and this is my y of n. Okay. Now, let us delay this signal by one sample. Let us see what is x of n minus 1. 0 shall be 0. I have shifted by one sample. So, I will start with 1 here, 2 here and 3 here. Okay. This is 0, 1, 2, 3. Agreed? Delayed by one sample. Let us see if this is upsampled by the same factor 2, what the waveform becomes. I shall have n equal to 0 shall be 0, then at n equal to 1 I shall have a 0, because between any two samples there is a 0. So this is 1. Then at 2 I shall have this signal, that is 1. 1. Then at 3 I shall have a 0. At 4 I shall have this signal 2, 3, 4. 5 there shall be a 0. And 6 I shall have this signal 3. Agreed? Does the waveform, is this one sample delayed by this? No, it has changed. The waveform has not been preserved. Agreed? If you sample this, if you delay this by one sample, at 1 you should have 1, which is not the case. At 1 you have a 0, and therefore an upsampler is a time varying system. Whenever you are in doubt for an analytical proof, you take an example, a very simple example that will clearly show whether the system is time varying or time invariant. Yes.
Sir, why don't you take this 0 in the whole zeros list and take 1 at 1 and then 3, 2, 0?
Well, that's not the case, because at 0 my signal range is 0 to 2. The question was, why don't you take this 0?
Yes.
No, this 0 comes because this system, this signal is delayed by one sample. It's delayed. You see, if your range of vision is only 0 to 2, you couldn't take this 3 either, isn't it? You have to take the total signal. Delay means you have started at n equal to 0, so n equal to 0, it is 0.
So 0 is a part of the signal after the shifting.
0 is yes, it's a part of the signal. The signal itself is this, 0 to 3.
But the signal is infinite, from minus infinity to
No,
infinity.
it is not. It's a finite signal. I have taken a finite signal.
Then what is the value of xn at value 3?
It doesn't exist. It's a finite signal of length. What is the length? 3. This signal becomes of length 4 by delaying by one sample. There is nothing else. It doesn't exist. For n less than 0, it doesn't exist. But if I delay it, if I advance it, that is shift to the left, then a signal will be created. So this waveform is not the same as this waveform. By delay, you have created a distortion. You have created two zeros before the first sample occurs. Okay?
But your waveform shape is still being figured, so it's not
Waveform shape is from here, not from here. Waveform shape is not from here.
it has been shifted in time by
Correct.
twice the
After this, it looks the same, but you have to take this also, that it remains 0 up to n equal to 2. I could have taken a little more
If you do
complete.
infinite sample, then
If it is an infinite sample, then also there will be distortion. You try one and be convinced. Take an infinite sample, delay it by one sample or two samples, you will see that again the waveform is not, output waveform is not one sample delayed version of y of n. You can you do this yourself. I could have taken a more complicated example to show that what you are thinking is not correct, but you can construct that. The next characterization, we talk of causality. A digital system is said to be causal. Let us understand conceptually what it means. A causal system is one which cannot predict the future. In human beings, there are people who claim to be non-causal. They can predict, they are called astrologers, right? And the roots are in the Vedas and Vedic astrology. It has come to be recognized as a course and all that. However, in electrical engineering systems, in systems that work, you see, prediction may or may not work, and usually all predictions are very positive, right? They never say you will meet an accident or you will lose money, and they say once in a while to make them credible. Don't believe in all this. There are no no basis, no scientific basis of this. This business of stars, getting together in a particular thing and all that. There is no scientific basis. Till there is scientific basis, I refuse to believe in this. But in electrical engineering system, it cannot predict what will come in the future, and that is called a causal system. So another name of causal system is also a realizable system. A causal system is realizable. So formally the definition is that y of n, the present output depends on the present input, depends on xn, its past values, and perhaps also the past values of the output, that is x of n, then x of n minus I is any positive integer, and y of n minus j, where j is any positive integer, not negative. Suppose it depends on x of n plus 1, that means the system at the present moment predicts what will come one sample later. No, that is not permitted. We do not have a physical device which can advance time, we can only delay, there is no advancement. But then let us see what the formal definition is. Formal definition is, now in terms of formal mathematical language, it says that a system, a digital system is causal if and only if x1 n identically equal to 3 parallel lines, means identically equal to x2 of n for n less than some integer capital N, implies no, 2 parallel lines, implies if two inputs are identical up to a certain integer value of n, that is up to, we can make it less than equal to capital N, up to capital N, then the output during this interval must also be identical for n less than equal to n. What does it mean? It seems very interesting, but it means that if n, small n exceeds capital N, x1 and x2 may be different, then y1 and y2 will also be different. But so long as the two inputs are identical, what comes in future for x1 or x2 is not anticipated by the system. This is the formal definition and this is the interpretation. Let us take a very simple example and see whether the system is causal or non-causal. Suppose you have a system in which y of n equal to x of n squared. Is this causal? No, it is non-causal. Put n equal to 2, then y of 2 shall be equal to x of 4. X of 4 is yet to come, and therefore this is non-causal. Suppose you have y of n equal to, let us say, moving average system in which x of n plus x of n minus 1 plus x of n plus 1 divided by 3. This is also non-causal because y of n depends on x of n plus 1. Agreed? This is also non-causal. But then if we cannot realize a non-causal system, if all our systems are causal, why are you talking of it? Why are you making a distinction? Distinction arises because non-causal signal processing, please understand this carefully, non-causal signal processing is possible from recorded data. The geophysicist, for example, he goes to the field and records by seismographs the vibrations. He gets back to the laboratory and then analyzes it. Now when he is analyzing a particular output y of n, he knows what is going to come because it is a recorded data. Alright. So on recorded information, non-causal signal processing is possible, and in geophysics in particular, also in weather prediction, non-causal processing is possible. But you cannot realize this in hardware. Okay, it's a processing, data processing basically. Hardware realizations have always to be causal. You cannot anticipate what is going to come.
All signals in nature are causal.
All signals in nature are causal. Okay. Is it a comment or a question? Question. Are all signals non-causal? Okay. Formally, x of n, a signal x of n is causal if x of n is equal to 0 for n less than 0. All right. You have to start the signal somewhere, call that n equal to 0, and therefore the signal is causal. But then if you have values like x of -1, x of 0 and so on, this is a non-causal signal. All right. This is a non-causal signal. So for signals can be non-causal. That is, what is x of -1? You start your processing at n equal to 0, but you know the initial value also. It's the initial value. Okay. If you combine this, then it's a non-causal signal. Mostly we shall talk of causal signals. What I said earlier was causal system. Causal system cannot predict what will happen in future, but if you have recorded data, it is possible to predict. And if you have a signal which has initial values, you start your processing, whatever time you start, you call that n equal to 0. N equal to 0 is arbitrary. You cannot go back to the origin of time. That will require Stephen Hawking. Even he cannot go back in time. Okay. So wherever we start our processing, we call it n equal to 0. And a signal is causal if x of n is 0 for n less than 0. Our next concern is stability. Unless you want an oscillator, a digital oscillator, all digital systems to be useful have to be stable. There is no other way. And stability that we bother about in DSP is the so-called BIBO stability, that is bounded input, bounded output. So the formal definition is that a digital system is stable if and only if a bounded input x of n less than b of b subscript x, which is less than infinity. That's the way to show a bounded input. A bounded signal is one which is less than a certain number, which number is less than infinity for all n. If this implies that the output y of n is less than some other number by, which is also less than infinity. That is, if the input sequence is bounded, the output sequence should also be bounded. Y of n is equal to 1 by n squared, obviously is an unstable system. Okay. Let us take some examples. We take the example of the moving average system. Y of n is equal to 1 by m summation x of n minus k, k equal to 0, upper limit is capital M minus 1. Now if x of n is bounded by bx, we can have an equality sign, it does not matter, which is less than infinity. Obviously y of n shall be less than equal to 1 by m summation k equal to 0 to m minus 1. Let us put all of them as their bounded value, the uppermost value, that is bx. So this is simply equal to bx, and therefore this is a stable system. Is this clear? Is it clear? Less than equal to I have written, so I can replace all of them by their uppermost value. Even then it does not exceed bx, therefore it is a bounded input, bounded output system. Suppose my y of n is simply an accumulator going from k equal to 0 to infinity x of n minus k. Is this a stable system? No, because there are infinite number of samples. So, even if x of n is bounded, the output is bound to go to infinity as n goes to infinity. So, this is an unstable system. Okay. Now, let us talk about.
So, even if the value of xn after some interval is going to 0, even if the one is system unstable.
Well, then it's a finite.
So, we have added the 0.
Okay, okay, which means what the question is, suppose x of n exists between 0 and n minus 1, all the rest are 0. Is that what you are saying? Okay, this is obviously a stable system. Yes, but this implies if we have to go to up to infinity, you see, if this is the case, then we shall replace the upper limit by n minus 1. Any bounded sequence, unless it is characterized otherwise, will lead to a bounded sequence at the output if you do not go up to infinity. If this is the signal, then we shall go only up to n minus 1. There is no point in, there is no fun in adding zeros, right. So,
stability is inherently related to feedback.
Stability is inherently related to feedback, not necessarily. Not necessarily. I told you that if y of n is x of n by n squared, there is no feedback there. But of course, this can be written as a feedback system. It can be computed with feedback, okay? But it can also occur without feedback. Suppose the sequence itself is unbounded, then of course, output shall also be unbounded. But in general, what you are saying is true. Stability is inherently related to feedback. In a non-feedback system cannot usually be unstable. Then we talk of passivity. The concept of passivity is very familiar in analog systems. That is, the energy of the output cannot exceed the energy of the input. Okay? As a digital system is said to be passive if this criterion is satisfied, namely the energy of the output, which by definition is yn magnitude squared. Well, n can be for all possible values minus infinity to plus infinity, and the energy of the input is x of n magnitude squared, again n equal to minus infinity to plus infinity. The system is passive if the output energy is less than or equal to the input energy. In other words, the system cannot generate energy. RLC networks are passive. On the other hand, if you have RLC networks combined with op-amps or transistors, it can become active. Where does the extra power come from? The power supply. Okay, there is the digital system is also a passive system is defined the same way. If this inequality is satisfied with the equality sign, then we call the system as lossless. Okay, this is an artificial concept. There is no concept of energy in numbers when you are handling only numbers, but we have to introduce this concept because it facilitates mathematical treatment. We take an example. Suppose y of n is equal to some quantity alpha times x of n minus n. Then this would be a passive system if yes, magnitude alpha can be complex, if magnitude alpha is less than 1. On the other hand, if magnitude alpha is greater than 1, then it is an active system. we conclude this lecture in a couple of minutes with another example. Suppose you have a time reversal system, a digital system which simply reverses the time. Is it a linear system? Is it a linear system?
Yes.
Yes, it is. Linear, yes. Yes, superposition. You take x1 and x homogeneous. If x1 is 0, y of n is 0, and therefore it is a linear system. It obeys superposition as well as homogeneity. Is it causal? No, because put n equal to -1, then your output is x of 1, what will come in future. So it is non-causal. Is it time varying? It is time varying, it is not time invariant, because x of n minus n0 leads to, I beg your pardon, single arrow, leads to x of minus n minus n0, not plus. Okay, the trick is this: in such cases where there can exist a confusion, what you do is y of n, write it as x of minus n and put minus n equal to p. Then x of n, this is x of n, leads to. So x of n minus n0 shall lead to x of p minus n0. It is the argument which is delayed, and this is equal to x of minus n minus n0. On the other hand, y of n minus n0 is equal to x of, yes, minus n plus n0. These two are different, therefore it is a time varying system. Is it a stable system? Stable? Yes, of course, if x of n is bounded, y of n has to be bounded, so it is stable. Finally, is it passive? Yes, it is passive. Okay. In the next lecture, we shall talk about impulse and step response of a digital system and the correlation between the two. That's all for today.